Hello, welcome back. So this is the next part of the Chapter 7, Section 1 video on naming ionic compounds. These are still going to be considered binary compounds that we're going to talk about. This is the second type of compound we're going to talk about. In this particular type, we're going to use what we call the stock system of nomenclature. Typically, we only use this particular type of nomenclature. Again, remember that nomenclature means naming system. Typically, we only use this one in order to determine the names of of transition metal type compounds. So these are still going to be binary ionic compounds. They're going to be transition metals, so not group 1, 2, or 13 metals. And these are going to be the types of metals that require a Roman numeral. They require a Roman numeral because a lot of these different metals can have more than one type of charge. So we have to indicate if it's going to be a 2 or a 3, like in the case of our iron. Now, the Roman numeral itself indicates the type of positive charge. We also usually only use these with positively charged ions. So whatever the Roman numeral is going to indicate the amount of positive charge that the atom it's describing actually has. So in order to name these, we're going to follow the same steps we did in our previous type of compound, where we're going to determine the charge given the Roman numeral, or we can use the actual formula of something in order to determine what the charge is. In this particular case, we're going to write the formula for iron oxide. This was one that we saw before, but this one is actually the stock system using the Roman numeral for iron, which is of course a transition metal. So since we know that we're going to be combining iron 3 with an oxide ion, so this is the name we were given, iron 3 oxide, we know that there has to be an iron with a 3 plus charge, because that's what we were told, and an oxygen. And we know that oxygen, when it's a negative charge, has the ending IDE, and also typically has a -2 charge. Again, in order to remind yourself why this oxygen has a -2 charge, please go back and watch the first part of this section's video. We talked about the common charges, and oxygen has a common -2. Since we know there are charges, we're going to write them side by side, and then we're going to use that crisscross method to figure out what the actual final formula should be. So we're going to take the 3 that's attached to the iron, and we're going to crisscross it down to the subscript of oxygen, and we're going to take the 2 that is the charge on the oxygen, and we're going to crisscross it down and make it the subscript of the iron. And you can see down here that we end with Fe2O3. Because we've crisscrossed those charges. In this particular case, then we can go back and we can check it by actually multiplying out the charges. Remember, it should balance. The whole idea behind doing this crisscross method is that it makes a neutral compound in the end. And so that neutral compound for this particular example is going to be Fe2O3. Again, you can prove it to yourself since you know that the iron is a 3 plus charge. If there are 2 of them in this compound, that means 2 times plus 3 becomes +6, and then 3 times -2 becomes -6. +6 and -6 cancel out to be 0, which is the whole idea behind us writing a neutral compound. So just to kind of give you an example, here we have the compound chromium 3 and F-. The formula that we can write is going to be the 3 plus. Remember that we're going to crisscross the charges. The F-, the minus implies a -1. In this particular compound, the 1 is one that we don't rewrite. So in this case, we have CrF3. That's the formula. The name would be a little more complicated. The name here is going to be chromium 3 fluoride. And when we write it, hopefully we don't misspell FLUORIDE. We're going to make sure that we insert the charge, the magnitude of the charge, which is the 3 plus, after the metal itself, and then we're going to drop the ending on the anion and add IDE. All right, so here it's your turn. It says, what is the chemical formula for the compound made of tin 4 ions and chloride Cl- ions? Give yourself a second, pause the video. When you are done, go ahead and play, and we will move on to our next portion. All right, so that brings us to naming using polyatomic ions. A lot of times these are referred to as oxyanions because, in case you did not notice while you were writing your different cards, most of our polyatomic ions have oxygen in them. These are going to be a subgroup. So the idea of a polyatomic ion is it is many atoms that are combined and have a combined charge of, say, -1, -2, -3, +1, +2, whatever it might be. So many many atoms combined together that have an ionic charge. Oxyanions are going to be a subgroup of polyatomic ions that have oxygen within them. And so some elements are going to be able to do this, and they're going to be able to form more than one type. And so again, if you go through your different polyatomic ions, we can talk about a couple of patterns. The first is the 8-ite pattern. Whenever you see the term 8, so the ending of a polyatomic ion ending in 8, means it has more oxygen atoms than the thing that ends in ite. And so here's our first example, nitrate and nitrite. Nitrate has one more oxygen than nitrite does. And so we name them using the nitre, that's the N that is included. The 8 and ite imply that there are oxygen atoms present, and in the term of 8 it means this one has more than the ite one, which has a few less. Now it could have one less, it could have two less, it could have just less than the number of the 8 that you are looking at. This is just one of the patterns that you can notice. Another pattern is going to be one where there is more than 2 types of oxyanions. And there's only a couple of examples out there. I believe there's only one that you had to memorize on your list of polyatomic ions. And that would be the chlorite, chlorate, hypochlorite, and perchlorate ions. Now in front of us, we start with hypo. Hypo means 1, so hypochlorite is going to be the one that has 1 oxygen in it. In this case, we add the chlor because that's the actual nonmetal that's involved that isn't oxygen. So hypochlorite. Then we move over to chlorite, then chlorate because we're gaining in oxygens, and finally we end with perchlorate, which is the one that has the most oxygens. And this list should look familiar to each and every one of you. These are the polyatomic ions that you should be working on memorizing. You can be asked to name them. So I could give you the polyatomic ion and ask you to name it. You can be given a name and asked to write the formula, as you've seen in your daily cues. We will take a quiz over this at the beginning of next week. All right, so how are we going to write formulas using these polyatomic ions? Well, it's super simple. All we're going to do is follow whatever naming convention is required for the cation, so the first part, say the metal, the transition metal, depending on where it's located, could require a Roman numeral to come after it. If it's in group 1 or 2, you already know the charge, so you don't need to indicate the charge. In that particular case, if we're talking about something like potassium, which is in this case going to bond with a carbonate ion, those of you that wrote HCO3 on your daily cue today, that was not correct. It's actually CO3 with a 2- charge. When we name these, or when we write them, we are just going to take the whole polyatomic ion and put it in the formula. And we're going to treat the polyatomic ion like it's its own entity. We're not going to break it up. We're going to keep it together. So you will see that moving forward beyond this slide, that polyatomic ions will always be in parentheses. I endeavor to always put the whole polyatomic ion in the parentheses with the charge on the outside, so that when you write it, you can see that the charge is what actually becomes the subscript of the neighboring thing. So just to kind of reiterate here, you're going to see them written in several different ways. You're going to see them written like this. What you need to remember is that the SO4 is its own particular part of this bigger molecule. And so when we break apart K2SO4, for instance, we break apart the potassium ions into individuals, but we leave the sulfate ion whole. Same thing with potassium nitrate. We're going to leave the potassium ion alone, or it can dissolve on its own and remove itself from the overall species, but nitrate should always stay together. In other words, we will never see the nitrogen just kind of detach and leave the oxygens alone. We will never see the nitrogens detach and just leave the oxygens alone, and so on and so forth. In formulas, polyatomic ions are going to stick together. They're not going to break apart. All right, so then here we have an example. And like I said, those parentheses are going to be pretty important. And so here we're going to write the formula for tin 4 sulfate. So again, we're going to follow the naming convention for the first part. In this particular case, we were told tin 4, so SN is the symbol for tin, and the 4 is the charge we were given in the parentheses, the Roman numerals. The sulfate has a 2- charge, SO4 has a 2- charge. So we're going to write the SO4 in parentheses, and I'm going to put the charge on the outside. And the reason is because the next thing we're going to do is follow the rules where we crisscross the charges. So the 4 from the tin becomes the subscript after the SO4, and the 2 from the sulfate becomes the subscript of the SN. Down here, I've gone ahead and I've rewritten that particular formula. Now, one of the things to note is that when we talked about chemical formulas at the beginning of this section, we said we had to write the most reduced form. And so since these subscripts on the outside can be divided down, we're going to do that. Just be careful that when you do that, you don't divide the one inside of the parenthesis. Think of the thing inside the parenthesis as a rock you cannot touch. Do not try to separate anything inside of that. Leave it alone. So we divide everything on the subscripts, so the SN and the SO4 subscripts, by 2, and we get SN SO4 2. Now, just because we don't see it, don't forget there is a fictional 1 right there. All right, and that brings us to your practice problem, which is also the end of this particular lecture. We have one more type of compound to learn how to write, and those are binary molecular compounds, which we will cover in another video later on. All right, that's all. Have a great day.